let's dive into a technology that's literally everywhere, from the deepest reaches of space all the way down to the smartphone in your pocket. It's a pretty simple idea, really, but with incredibly powerful results. You just combine a bunch of small, simple things to create something much, much bigger and more precise. Welcome to the world of antenna arrays. You've definitely seen these pictures, right? These colossal dishes, all pointed up at the sky, just listening for the faintest whispers from distant galaxies. But what if I told you the real magic isn't just about building one giant ear? What if it's about using dozens of them together, like a single, super-powered instrument? Okay, check this out. This is the Very Large Array out in New Mexico, and it's the perfect example. See, it's not one giant antenna. It's a whole team of them, all working together in perfect sync. And together, they can do things that no single dish, no matter how big, could ever do on its own. Now that's the power of an array. So why go through all this trouble? Why bother combining all these antennas in the first place? Well, it all comes down to one single thing: focus. Creating a highly focused, super directional beam. Let's dig into why that is so incredibly important. You know, it really comes down to two big reasons. First, when you're trying to communicate over just vast distances, we're talking satellites, deep space probes, that kind of thing, you just can't afford to waste energy broadcasting in every direction at once. You have to aim your signal like a laser beam. And second, when you're on the listening end, trying to pick up a super faint signal and you know exactly where it's coming from, you want to point all of your listening power in that one direction and just tune out all the other noise. So how do you get that laser-like focus? Well, you could try to build a single, impossibly massive antenna. Or you could get smart about it. You can take a whole group of smaller antennas and get them to work together as a team. It's all about strength in numbers. All right, this is where it gets super cool. The way these antennas cooperate isn't just about throwing more hardware at the problem, it's about harnessing a really fundamental principle of physics. The core idea is actually surprisingly simple. The total signal that you get from the array is just the sum of the signals from each individual antenna. But hang on, it's not just simple addition. It's about how the waves themselves combine. And that brings us to the key concept, interference. Think about it like ripples in a pond. If the peaks of two waves meet up, they join forces and create a bigger, more powerful wave. That's what we call constructive interference. But if a peak meets a trough, they flatten each other out and just cancel. That's destructive interference. And antenna arrays are absolute masters at controlling this effect. So look at this diagram here. See how the two antennas are in slightly different spots? That means the waves they send out have to travel slightly different distances to get to that faraway point. And that tiny little difference in the path they travel, that is everything. It's what decides if the waves are going to add up or cancel each other out. So here's the entire goal, the whole point of an antenna array. It's to cleverly arrange the antennas and their signals so you get this massive constructive interference, a super strong signal in the one single direction you care about, and destructive interference, basically silence, in every single other direction. And this isn't just some happy accident. It's pure, beautiful math. Engineers have what's essentially a master recipe that lets them control this interference with incredible precision, telling the beam exactly where to go. Okay, so that's the big idea, but how do you actually do it? How do you turn this amazing physics principle into a steerable beam of energy that you can actually control? The answer is something called the array factor. This is the mathematical key that unlocks the true power of the whole array. Now, I know this looks a little intimidating, right? But all this formula is really doing is what we've been talking about. It's adding up the signals from every single antenna in the array, from number 1 all the way to n, however many there are. It's just taking into account the position and the timing of each and every one. But here's the beautiful part. Through the sheer elegance of mathematics, that long, complicated sum boils down to this one single, compact equation. This is the array factor. It's the master recipe. By plugging in the number of antennas, how far apart they are, and the timing of the signal, this formula predicts exactly how the beam will be shaped and exactly where it will point. It's basically the control panel for the entire array. All right, so that's the theory. Now let's see where this incredible technology actually shows up in the real world. And trust me, once you start looking for it, you're going to see it everywhere. So we're back where we started, at the Very Large Array. But now we know it's not just a collection of dishes. It's a precisely controlled array, using that array factor to combine all their signals and create a virtual telescope that's literally miles wide, giving astronomers this breathtakingly clear view of the universe. And here it is, right in your own neighborhood. Ever really look at a cell tower and see those rectangular panels on top? Yep. Each one of those is a sophisticated antenna array. They are constantly using this exact technology to shape and direct beams of signal, making sure to provide coverage precisely where it's needed to connect your phone to the network. But arrays don't have to be gigantic. This is a patch antenna array, printed right onto a circuit board. You'll find these inside modern radar systems, high-speed Wi-Fi routers, 5G equipment, you name it. It's the same powerful principle of cooperation, just shrunk down to a crazy small scale. In the end, it really all comes back to this one powerful sentence. Everything we've talked about, from the VLA listening to the cosmos to the cell tower connecting your phone, it's all an application of this fundamental truth. You add the individual parts together in just the right way to create a whole that is so, so much greater. And that kind of leaves us with a pretty cool question to think about. This principle of the array, of combining simple elements to create a powerful, steerable sensor, it doesn't have to stop with radio waves. What if we applied it to arrays of microphones to perfectly isolate one voice in a giant crowd, or arrays of optical telescopes to see even further into the universe? The idea of strength in numbers is an incredibly powerful one, and we are just beginning to explore where it can take us.